Do you know how personalized recommendations work in the digital space? Like how Netflix recommends movies based on your previous watches. The same thing happens when you're shopping online. The product you browse, click, or purchase leave behind the signals about your purchases. Well, the recommendation engine behind such systems are fairly complex, and what we are going to discuss today is the key idea which powers them. And not to mention, it's also one of the building blocks of every LLM that we use today. Hi, I'm Jyotsna and welcome to the Hidden Layers. Today, we are going to talk about embeddings. So first, we are going to see through examples what the intuition behind embedding is, and then we will cover techniques which are widely used to create embeddings of word vectors. Soon after that, we'll do some hands-on and learn how to build our own embedding model from scratch. And then we will wrap up by understanding why a new kind of embedding became so popular. Let's understand from the example of Netflix and how it actually recommends TV shows. Suppose every TV show on Netflix can be described by a set of characteristics, and say for example in our case we have 5 of these characteristics: sci-fi, mystery, comedy, darkness and supernatural. Now as you can see, I have assigned some random scores to each of the TV shows. Don't worry about the numbers. I have also color coded the scores, so see if it makes sense to you. Now, since we have these 5 different features, we can represent it in a 5-dimensional space. But you see the problem? It's really difficult to visualize something in a 5-dimensional space. So in order to simplify this, let's just pick 3 out of these 5 different characteristics. We can represent these XYZ as sci-fi, supernatural and mystery. Now, let's plot the points. Do you see a pattern here? Pause for a second and think. Yes, Dark and Stranger Things ended up close together, which is also quite evident from this table. As you can see, these two score high on 3 out of 5 different characteristics, which means that they share quite a lot of similarities. Now, let's come back to our table. We can also call this an embedding matrix. The number of rows here represent the number of items, and the number of columns represent the number of characteristics which we have at hand. Let's call them V and D, where V is our vocabulary size, D is called as embedding dimension. Now, we will try to find the embedding of one of these items. Say we choose friends. Since computer doesn't understand text, we need a numerical representation for it. And so, we assign every index value as 0 except for the second index, which represents friends. Now, on the left hand side, we have what we call as one hot encoded vector, which is represented by X. And on the right hand side, we have our table, or we can call it our embedding matrix. And in order to find the embedding for friends, we use this simple formula, which is y equals x multiplied by e. And this is basically our matrix multiplication. Don't worry much about the calculation, as we will soon see a shortcut to find the embedding. But for now, let's try to multiply it and see what we get. So, how we find this value? We multiply this x vector with each of the columns, and what we get as a result is a single vector. So first we take the dot product of x with the first column, which gives us 0. Next, second column, that gives us 0 as well. Then we take dot product with the third column. Similarly, taking dot product with the fourth column gives us 1. And the last column again 0. So now we have found the embeddings for friends. And you might have already noticed that this is exactly the third row in our embedding matrix, which is exactly the shortcut to find embedding which I mentioned earlier. And this exact idea is also used by the standard libraries to find embeddings for a certain word. And note that we have been playing with a single example of these TV shows, but the same idea applies to a lot of different things, like words in a language, or images, or any kind of entities where we can benefit from finding the similarities between two different items. And this exactly is the core idea behind embeddings. Earlier, we saw through movie recommendations example how embeddings help us find similar things. But you might be thinking, how can a computer assign those scores to each characteristics without us feeding that information manually? Well, that's the beauty of machine learning. As the model converges during the training, it gradually learns how to encode the words so that similar words end up close to each other in the embedding space. And here's the fun fact, we don't even have to decide what features we want it to learn. The model can identify those characteristics on its own. So now, let's understand how to create embeddings for English language words. Say we have these 5 sentences. Now pause for a second and just try to read the sentences and see if you can find any similarities. Do you see that first and third sentence, I saw cats running in the street and I saw dogs running in the street, are almost same except for the words cats and dogs. Now this means that in our training space of 5 examples, cats and dogs appear in similar kind of context. And this exact principle is used to train word embedding models. And one such widely used technique which leverages this idea is called word-to-vec. Now, word-to-vec trains an embedding model in two different ways or architecture form: skipgram and continuous bag of words. There is just a minor difference between the two, where skipgram tries to predict the context words given the center word. Continuous bag of words focuses on predicting the center word given the context words. So it's just the training objectives are reversed. So now we can just focus on one of these techniques to understand the training process. And let's pick continuous bag of words. Let's create the training data for our 5 sample sentences. As you can see from the right side table, I have picked 2 context words, one from the left and one from the right of the center words. And the targets for these are the center words, which means that we try to predict the target words given context. And now, before we begin the training, we initialize these 2 embedding matrices, one for the context words and one for the center words. Note that we will have all the words present in our training corpus as part of both context embeddings and center words embeddings. The reason is of course because every word can be the context for the other words and vice versa. And don't worry about the numbers which you see here, these are just random initialized numbers which are going to be adjusted as we train the model. So now let's just focus on these 3 words: cats, car and dogs. The reason is simple, cats and dogs share some sort of similarities, while car should be far from them in the embedding space. We will see this in action in the coding section in a bit. But before that, let's see the training process. I know, this looks way complicated than what we have been seeing so far. But if you will follow along with me, you will realize that it was not so complicated to begin with. So now, as a first step, we have already created our training data. And now, in order to build the feature to predict our target word, we take the context word pairs and take an average of both. What we get here is a context signal, which we now use and find dot product with each of the words in the vocabulary. But remember that the second word's embeddings will come from the second matrix, which was the center word matrix. So to repeat, we find the average context signal for each training data using the context word embeddings from the context matrix, and then we try to find its similarity with each of the words in the vocabulary using the center word embeddings. Note that we take dot product here because it's the easiest way to find similarities between two vectors. And now if we have n words in our vocabulary, we will get n different scores. And now we apply softmax function over these raw numbers to get a nice probability distribution over the scores. And what are these probability scores? Well, they are just indicating that which is the most likely center word given a context. If you are from a machine learning background, you might have realized that this is a standard multi-class classification problem. And if you are not, don't worry, which you can refer to understand all the different kind of concepts which we are discussing in this training process. So now let's move forward. We have already calculated our model output, and now it's time to optimize the model. As a standard method, we try to optimize a loss function. And again, multi-class classification problems usually uses cross-entropy loss, and so we use it to calculate the gradient for each of the embedding parameters. We iterate this process for n number of epochs until our model converges, or so to say that our model training loss minimizes. I know, this was quite a lot if you're new to machine learning, but I would highly recommend reading the document in the description. And then if you revisit this particular section, things will become much clearer for you. But for now, let's start with the fun part. There are many pre-trained models available today, but it's always fun to build something on your own. So let's get some hands-on experience. Note, if you are new to Python, you can also follow along. But if you are trying to build a career in AI, learning Python will always be very helpful. Now, before we start the training process, if you have Python installed, then all we need is to install these two libraries. First is Torch, and then we have NumPy. And if you haven't worked with these libraries, then don't worry. NumPy is a library that just makes it easier to work with vectors, matrices, and numerical computations. And PyTorch is just a deep learning framework that helps us to build models and train them and provide some additional functionalities for it as well. So let's proceed with installing them. And you can use these two commands to install it. So I'll just run this. So I have already installed these. Now, the first step is data preparation. In order to prepare the data, first we create tokens out of these sentences. The simplest way you can think of it as breaking down the sentences into words. So for now, let's just split the sentences into words. But even before that, let's just join all these list of sentences. So we have just one big corpus of text data. So in order to do that, I'll just join the sentences. So maybe text data equals, we just join the sentences with a space. And I take these sentences. And now we have this one big corpus. We can just create the tokens out of it. Let's take this and we split it. And then tokens. We get all the words present as a list. And so from now on, we can also call this list of tokens as our vocabulary, which is also a standard terminology to follow. And so you can also notice that some of the words or tokens are also repeating, like in, here, and then the. So now let's just create a set out of it to just get a unique set of words as our vocabulary. I am also sorting it. So let's just check the length of our vocabulary. Okay, so now we have 16 words or tokens in our vocabulary. As a next step, let's just provide them IDs, like numerical identity to each of the token, and we will see why we need it soon. What we will do, we will create two mappings, each word to their corresponding IDs, and then we also create a decoder map so that we can get back to the words from those IDs. So first, let's just create the word to token ID mapping. And secondly, we will create the reverse mapping. I to W. Now let's just see how these two look. So as I was saying, we have these word to their token ID mappings and then the vice versa. And why we do this is words is as good as their token IDs because it neither understands the word nor this ID. What is actually going to be meaningful is what we actually get as word vectors out of them once we train the models. So the first step of data preparation is done. Can you think of the second step? Yes, we need some sort of a context words pair mapping to their target words so that we can provide a task for our model to train on. So now let's just create out of these sentences the mappings of their context pair of words with their center word. For example, soy and running are our context words and cats is our center word. And here I have already created a script to do that. So let's just go through it. So first we initialize a list called pairs and then we go through the sentences one by one. We split the sentence to get all the words present in it and then we iterate over the list of words ranging from the first index till the last but one. Why this? Because if you come here, our first set will be something like this. So we need offset of 1 because if we had started right from 0, then it would have errored out because we do not have a previous index. So we start from 1 and for the same reason, we also stop one place before the last index. So now our context word for any given I is I minus 1 and I plus 1th index words and then our target is our center word. And this is how we prepare our features for model as well as their targets. And now if we see our pairs, yes. So this is exactly like the table data we have here, soy and runny and then the cats. So similarly, we have all the context and target pairs created here. So great. Our data preparation is now done. Now let's just look at how we exactly build the model architecture. So now let me just inform you, if you are new to PyTorch or you haven't worked with any machine learning framework before like TensorFlow or scikit-learn, this might not click in the first time. However, I will still recommend to just keep following because this will still give you some intuitive idea about how we build a deep learning model. And for your reference, I will also attach another document in the description, which will provide a quick start guide to you in order to build any kind of deep learning model using PyTorch. So we always build a PyTorch model starting from defining the class. And even before that, the first step would be to initialize the libraries, import torch, then import torch.nm as we just give an alias to it. So we are also going to utilize optimizer. So let's just import it. And if you have the PyTorch library installed, this should work for you. Great. And now we start defining our class. So now you might think, why this nn.module? Well, this is because we want PyTorch to recognize this class as a trainable model architecture class. Okay. Okay. So now we initialize our class. Let's just initialize our superclass nn.module so that we can inherit all its functionalities. And this is like a standard way to initialize our parent class. Okay, so now you might question, what do we initialize here? So what inputs we would want to initialize this model? Yes, so we need the vocab size as well as we need an embedding dimension to be specified, right? And you may question, do we need only 3 embedding dimension? But no, We can decide upon any number of embedding dimension. We will cover a video later on this topic, how exactly to choose the right embedding dimension for your use case. So what two inputs you should actually provide to this? So first is the embedding dimension and second is our vocab size, which is like the number of words we have in our training data. Now we define our embedding layer. Embed equals. So PyTorch already provides an NN embedding layer, which is basically just a thin wrapper around this kind of matrix. NN.embedding. And again, what should be our x and y dimension? So our number of rows would be our vocab and the columns will be our embedding dimension. So we just provide both vocab size, embedding dimension. Great. And what do we need as our second layer? Just a linear dense layer which can classify our center word given the context. And input to this would be embedding dimension because that was the output of our previous layer. And the output for this, well, this layer will provide an output for each of the words in our vocabulary. So let's just say vocab size here. So now if you're familiar with PyTorch, we know that the next step is to define the forward function. Input to this forward layer will be our context words indexes. So let's just say context indexes. Okay. And so first now we pass these context index input through the embedding layer. So now what we will get out of this are two rows, let's say saw and running. So the dimension for this will be, let's say we also have batches of input. So we can say that batch and then two rows, so 2 and then our dimension. So let's just call it D, which is our embedding dimension. And so now, as we've already seen in the video previously, that we take an average of these two context vectors to get a single context signal, right? So we do that here, like let's say context, maybe signal equals, we take the mean of it, right? Mean. Now we need to provide the dimension. So we need to take the average on our columns so that it takes the average of saw running on dimension 1, then dimension 2, and then similarly for 3. So we provide dimension as 1, right? Which is like column. Okay, so next we just return the after passing it from the linear layer context signal, right? So this is our model architecture. So let's just initialize it. So we have our vocabulary. So now the inputs goes in our vocab size and embedding dimension. We have our vocab size here. So we do maybe vocab size equals n, and then we take, and now our embedding dimension, let's just say 8 for now. And now as a next step, as we discussed previously, we need cross entropy loss function for this. So let's just initialize it. Right. And now we need an optimizer and we need a learning rate. Let's just say maybe 0.05 for now. Okay. Oh, we have an error. Super has no attribute we need. Okay. Okay, we have a typo here. Sorry. Now let's run it again. Okay, now the model compiles. So before we proceed with writing the model training code, we also need a way to check how, let's say, these words cats and dogs are going to end up close to each other. So we use cosine similarity in order to do that. So I have a simple function for cosine similarity which can help us do that. Cosine similarity is nothing but taking the normalized dot product so that we can know how much two vectors are similar to each other by checking the angles between them. Right. So now we can proceed with model training. So I've already added code here for model training. So let me just go through it step by step. First of all, we are focusing on just these two words, cat and dog. just to see how their similarity score converges. And then I have just initialized a list called history here, which is just to log all the losses. And then we can just iterate through 200 epochs here. So now we can just like loop over the training data points, and then we just convert our context pairs into our PyTorch tensors. This basically just helps in faster computation. Similarly, we can just convert target as well into Torch tensor. We pass it through the model for the forward pass. So we provide the context pair of integers to model. So basically we pass these two indexes of the neighboring words. We get our raw scores, which we also call as logits. So now you can imagine the output shape from this layer for logits, which would be just a single row with a probability score over all the words in the vocabulary. So we can say V. Great. Now, as we already have the model output from the forward pass, we can calculate the loss using this loss function, which is our cross entropy loss, right? And then we add this line to clear all the gradient calculation from the previous steps. So since this is going to iterate over loop, PyTorch tends to accumulate the gradients, and we do not need that because we need a fresh set of gradient calculation for each epoch. So we add this line, and then loss.backward calculates the gradient over each of the embedding parameters and the dense layer parameters. So once the gradients are calculated, we just add this line optimizer.step, which actually updates the weights based on the gradients which we have calculated. So if you're not familiar with this, don't worry. Again, like you can refer to the document in the description on how to train a PyTorch model from scratch, and then you will get to know about this. But this is a classic way to train a model using gradient descent. So just to reiterate, we first started this looping over the epochs. Then we started this iteration to get each training pair from the pairs which we had created before. Then we created the tensors out of both context and target words for forward pass. Then we calculate the logits by passing in the context to the model, and then we calculate the losses based on the loss function we have defined earlier. Then we just do the sanity of clearing the previous gradients. And then we calculate the partial derivative or gradients for all the parameters we have in our model. And now this step basically updates our weights. And now we just like accumulate the total loss here. Okay, so now we start our model training. And now using this, we see how our similarity scores change. Okay. So now, interestingly, as you can see, the cosine similarity changes so much over the epochs as the model trains. So it starts with just zero point 0.1, it goes to 0.7, then 0.83, and then it improves all the way till 0.9448, which is like a great improvement. This basically tells us how model actually brought these two words together given the context of data which we had given. Now, let's quickly recap what happened here. We started with plain text sentences and converted words into numerical IDs because neural networks can only work with numbers. Then we created this continuous bag of word training examples where the model looked at the surrounding context words and tried to predict the missing center word. And then we defined the model architecture by seeing this example where all these initial embedding weights were randomly initialized. And then we defined our cosine similarity in order to basically calculate the similarity between two words as the model converges learning. And then through many rounds of predictions and error calculations and weight updates, the model vectors gradually adjusted themselves. And since cats and dogs appeared in very similar context, their vectors moved close together in the embedding space. Which is what finally we witnessed through checking the similarity scores as it improved over time, starting from 0.11 to 0.95, which is basically 95% similarity. And now this was all about embeddings and how you can train your own model from scratch. Say you're using ChatGPT and you have these two different kind of questions in your mind. Summarize this book in 3 sentences. How do I book ticket for the World Cup? Now you see that both the sentences has the same word book with two different meanings. Now in order to answer these questions, ChatGPT will first have to infer their meanings. And by that, we can imagine that it might be using a word embedding matrix to get the vectors. And now can you see the problem here? We have just a single row vector for the word book, but it has got two different meanings. So what's the solution here? We need a way to represent a word in an embedding space so that it gets its meaning based on how it's actually used in a sentence. And that's how contextual embeddings come into picture. So in the next video, we will discuss about it in detail. We will also see how we can represent an entire sentence or even a document using just a single vector. So stay tuned. And that's all for today. I will be making videos on this channel on a weekly basis. So if you want to stick around, make sure to subscribe. Okay, bye.